Dripping down science. The Naked Scientists.
Hello, it's Sunday the 23rd of October. Welcome to The Naked Scientist this week. I'm Chris Smith, and also here with us are plant scientist Emily Seward. Hello, Emily.
Hello.
And also naked astronomer and space scientist Dominic Ford. Hi, Dominic.
Hi, Chris.
Now, it's our science phone-in this week, and very shortly we'll be finding out what it is that makes ice slippery. Sounds simple, but it's got scientists baffled and has had for a long time. And also, can you start a fire with moonlight and a magnifying glass?
And we've got news this week of a breakthrough in treating chronic fatigue syndrome and why taking an antiviral a day could keep Alzheimer's disease at bay.
Plus, we've got a cool kitchen science experiment for you to try out. You'll need a bottle, a coin and a freezer.
So, if you'd like to get in touch with your science questions and your comments, you can tweet at Naked Scientists, or you can write on our Facebook page. That's at facebook.com/The Naked Scientists, or you can, of course, drop us an email. Our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
We're off to a roaring start with our science phone-in. Sinead's on the line. Hello, Sinead.
Hi.
I understand you're in Cambridge.
Yeah, I'm at Emmanuel College.
Very good. So we're replacing the university as your source of education. That's good. What can we do for you?
Exactly. How do plants tell which season it is? And I was just also wondering whether the warm weather we've been having lately will confuse them.
So that's a really good question. I've been confused myself. I went from flip-flops to winter coats and back again. And I think that it's even more important for the plants to know when winter is. They can't just nip to the shops. They have to have reserves for winter and know which season is coming so that they can prepare. And they do this by measuring day length. So they can know that if you've got a lot of nighttime and not very much day, then you're in the middle of winter. And of course, the other way around as well. So if you've got a lot of sunlight and not very much nighttime, then it's in the middle of summer. But you can imagine that spring and autumn would be a bit of a confusing area because the day length can be very similar and it's very different. In springtime, you're waking up, you're sprouting, you're making flowers, whereas in autumn, you've got to do the opposite. You've got to lay down reserves and get ready for winter. So plants have a mechanism to deal with this called vernalization, and it's where they require a prolonged cold period before they'll germinate or flower, and this will stop them making new flowers in autumn when they should be getting ready for the winter. And it's surprising how hardy and resistant most plants can be to extreme cold. You can get willow trees that can tolerate liquid nitrogen, so minus 196 degrees C. If they're prepared, you can't just dunk them in it. They have to have time to make cryoprotectants and also antifreeze proteins. But then they're able to really deal with it very, very well. So I would say that, yes, the plants will have been a little bit confused. You might have seen some roses resprouting and the buds they've made will die. But most of them are able to judge the day length and actually deal with it very well.
I've got a spring plant in my garden that should flower in April, and it's come back into flower again. Presumably because we had that cold snap a little while ago and it now thinks, hey, we've had winter, now it's time for spring again.
Most of them require a bit of a longer period of cold than that, but yeah, it's probably thinking, I'll give it a go, and if the buds die, then the buds die.
That must be bad for the plant, though, because presumably it's eating into reserves it's built up over the summer that are now going to be used to sustain it over the winter, and they won't be there.
It's not ideal, you're right, but it's not the end of the world, so the plant will have enough reserves. Normally it can store them in tubers and that sort of thing.
Good stuff. Hopefully that sorted things out for you, Sinead.
Yeah, that's great.
You've got a
Thanks
pot
very
plant
much.
on your windowsill?
Thinking of getting one, but trying to find one that won't die immediately.
Maybe Emily can give you some advice. Thanks for joining us on the programme. Good
Thanks very
question, by
much.
the way. Great to have you with us. Luke's with us. Hello, Luke.
Hello.
You've got one, I think, probably that's going Dominic's way. Fire away.
My question is, how large of a magnifying lens would you need in order to focus enough moonlight to start a fire?
Well, that's a really interesting question. It's not one that I thought about before. But there is actually a limit to how much you can magnify the light of an object with a lens, because there's a fundamental law of optics that says in order to make something appear, let's say, 10 times brighter, you have to make it appear 10 times bigger in the sky. So when you use a magnifying glass to make the sun appear perhaps 30 times brighter to set fire to a piece of paper, what you're actually doing is making the sun appear to take up 30 times the area of the sky from the piece of paper's point of view. Obviously, you reach a hard limit when the sun's rays are coming from all directions in the sky towards your piece of paper. And it's perhaps interesting to ask what temperature your paper would reach if you had a lens that could do that. And the answer is the paper would see a view of the universe just as if it was embedded in the surface of the sun. And so it would reach the same temperature that the surface of the sun is at about 6,000 degrees C. Now, moving that to the moon, the surface of the moon has an average temperature of about minus 50 degrees C. So that's actually quite cold. So even if you covered the whole sky with moonlight and had no sun, your piece of paper would reach temperature minus 50 and no warmer. So no, you couldn't use the moon to set fire to a piece of paper. There is an interesting extension to that because, of course, we think of stars as being much fainter than the moon, but stars are also much smaller. So if you magnify the light of a star up to fill the whole sky, you would reach the temperature of the surface of that star, and you could potentially use a star to set fire to a piece of paper. And in fact, there is a paper that was published by Donald Lyndon Bell in 2002 with the design of a telescope for doing exactly that.
Gosh, so Luke, you might be in luck with a telescope, but your magnifying glass and moonlight ain't going to cut it, I'm afraid.
Okay.
Someone like Rod Stewart or someone like Tina Turner might be bright enough, who knows. Now, Dominic, I'm quite glad you sort of launched into outer space, because tell us about this news story that's come up this week, because the Herschel Space Observatory is already beginning to turn out really interesting data, and there's this one that I saw written up where they've actually been looking at water in a disk around a star. Tell us about this.
That's right. It seems our solar system may not be alone in having an abundant supply of water, and that's according to a paper published this week in the journal Science. Now, this is by Mikkel Hogerheide at the Leiden Observatory, and he's pointed the Herschel Space Observatory at a star called TW Hydrae. Now, this is a very young star. It's only about 10 million years old, and it's really still forming, essentially, and we think it will in due course form a star about 60% of the mass of our own sun. But what's really interesting about this star, as well as the fact that it's really very close to us and it's very easy to study, is that it's got this disk of gas and dust around it that we call a protoplanetary disk, and that we think will form into a planetary system around this star.
It's quite interesting because it kind of gives us an idea as to how we got here.
Yes, and obviously an interesting question to ask is this planetary system going to turn out to be similar to our own solar system? And one of the important characteristics of our solar system, certainly from the point of view of it being possible for life to form in it, is that it's got abundant water. Water is very important for life, obviously. So in our model of how our own solar system formed, we think there was water spread throughout this protoplanetary disk, and close in towards the sun, that would have been in the form of water vapour, because it would have been too warm for that to be in the form of ice. It would have sublimed or boiled into a gaseous form. But then you would have a line that we call the ice line, and outside of that line it would be too cold for it to be in water vapour. It would be in lumps of solid ice. And that's why you have asteroids in the asteroid belt, which are dry, and you have comets in the outer solar system, which are wet, dirty snowballs. And the Earth formed, obviously, nearer towards the sun than that ice line, so it formed initially as a dry planet, and we think the comets in the outer solar system are very important in bombarding the Earth and bringing water to the Earth to make it habitable. Now, looking at TW Hydrae from the outside, previously people have seen that water vapour in the inner part towards the star, but they haven't been able to detect the presence of ice further out, and the reason is essentially spectrally it's quite difficult to detect solid ice. But what Hogerheide has done is he's realised if you got these solid lumps of ice and you've got ultraviolet light impacting on those solid lumps of ice, you'll knock occasionally water molecules off those lumps of ice, and that will go into cold water vapour around those lumps of ice, and you could potentially detect that. And he has detected that water vapour in this disk. And there's no way that could have formed by thermal boiling. It must have formed by this ultraviolet mechanism. So although he's only detected a small amount of this cold water vapour, it suggests there's several thousand times the amount of water in all the oceans on the Earth in this planetary system. And it's got good potential to form planets that might be habitable.
if you're going to live long enough to go and live on one of them.
Yeah, it's going to be a few million years, I think, before this forms planets.
Dominic, thank you. You're listening to The Naked Scientist with Chris Smith, with Dominic Ford and Emily Seward. It's our science question and answer show this week, where you send in the questions and we have a go at answering them. If you go to facebook.com/The Naked Scientist, we've got lots of questions coming in there, and you can also tweet at Naked Scientist, as has Martin Probert, who says, how does fly spray work? Good question. Well, fly spray, this is the stuff you spray on the fly, and it usually... there's a short lag, and then suddenly the fly appears to go nuts. It speeds up its activity, and then all of its movements appear to become very chaotic, and then usually it ends up laying on its back with its legs writhing in the air, buzzing furiously, and then it just expires. What's actually happening is that the fly spray is a neurotoxin. It's got chemicals in it that inhibit an enzyme in the body of the fly called an acetylcholine esterase. And this enzyme is very important for interrupting the flow of information between motor nerves and muscles. The nerves squirt out a nerve transmitter chemical called acetylcholine. This binds to special docking stations called receptors, which are on the muscle and activate the muscle. And then you terminate the signal by breaking down the acetylcholine with this acetylcholine esterase enzyme. If you inhibit the enzyme with the drugs or the chemicals that are in the fly spray, then what happens is that you end up stimulating the muscles too much, you don't interrupt the signal, and as a result, the fly's muscles all go into tetany, they're contracting all the time, and as a result, the fly becomes non-viable, and it also can't move its abdomen backwards and forwards to move air in and out of its body, so it can't oxygenate its haemocoel, the bag of blood inside the fly, so it basically asphyxiates as well. So that's how fly spray works. Now, quick one for you, Emily. Shelley has said, will bananas brown faster on the counter or in the refrigerator? So should you put your bananas in the fridge?
Well, it's a good question, and the answer is that they will brown faster in the fridge. It's mainly due to the formation of ice crystals. So you put your banana in the fridge, the ice crystals grow, and they actually rupture the cells of the banana skin. And this releases an enzyme called polyphenol oxidase. And as the name suggests, it acts to oxygenate phenols, which have a ring-like structure, into quinones. And these quinones can then all join together or polymerize and produce a black or brown or red pigment called polyphenol, and this is what gives it the brown colour. So if you have your banana in the fridge, this will occur and you'll get a brown banana. But another interesting thing about bananas is that if you have them in the fruit bowl, they'll release ethene, and this will make the other fruits in the bowl ripen faster because it's a ripening hormone.
So the question is, though, if this is a chemical reaction making this brown pigment, if you slow down the reaction by lowering the temperature, then it should happen more slowly. Therefore, going in the fridge should make the bananas go black slower?
I can see why you're thinking that, but actually it's more the rupturing of the cells. So if you have a banana on your table, the cells are going to be intact, the enzyme's contained, and the reaction's not happening at all. Whereas if you put it in the fridge, the enzyme's released and the reaction can happen, although yes, it might happen slower.
Brilliant, Emily, thank you. We heard from Robert McCulloch on Facebook. He says, just want to say how much I'm enjoying the show. Keep up the great work. So if you would like to send in a question, you can also go to thenakedscientist.com/Facebook. More questions on the way.
Keeping you abreast of the world's best science. The Naked Scientists.
And in case you're wondering who's answering them all for you this evening, I'm Chris Smith. We also have Emily Seward, who's a plant scientist from Cambridge University with us, and Dominic Ford, who is a space scientist with, I think you have a special penchant for how stars work, don't you, Dominic? Is that your particular area of expertise?
Yeah, stars and planets are quite fun.
Quite a big subject. Well, anyway, if you would like to do some experimenting now, Emily?
We're going to go join Ben and Dave and learn a new trick for that spare change in your pocket.
I have returned to the spiritual home of kitchen science. That's Dave Ansell's kitchen. And today we're going to do an experiment that we have to do in a kitchen because we need a piece of equipment that generally you can't carry around with you, and that's a freezer. Now, Dave, what are we going to do today?
Okay, so what I've got, as well as the freezer, which is sitting in the corner of the kitchen, a couple of lemonade bottles, so fizzy drinks bottles. I'm using half-litre ones because that's all that will fit in my freezer upright. A 2-litre bottle would actually probably work better, but unfortunately I don't have a chest freezer.
Does it matter what sort of drink it is? Does it have to be fizzy?
It will work slightly better with a fizzy drinks bottle because they're a bit stronger, but it'll probably work with a water bottle or something similar as well. We're actually going to do this with empty bottles, And in fact, I've got a couple of empty fizzy drinks bottles in the freezer, cooling down. They've been down for about half an hour. They should be nice and cold, down about minus 18 degrees centigrade.
And is that with the lid on or the lid off?
With the lid off, although I should have one which I left the lid on, so we should see what's happened to it.
Okay, so we're cooling down empty, open bottles. So far, this doesn't really sound very much like an experiment. But the one with the lid on, Dave has just taken out of the freezer, and it looks like it's been crushed. Did you do that before you put it in?
It started off completely inflated, and then in the freezer, it's kind of crushed itself.
Okay, so something about being in the freezer has caused this plastic bottle to pull in on itself, to compress itself. But the other two don't have the lid on, so presumably they're still the right shape.
That's right. What's going on is the air inside the bottle is a gas. It's made of little tiny particles which fly around the place. They only take up space because they bash into the sides. They bash into things. When they bash into things, they push on them and they exert a pressure. The hotter something is, the more energy it's got, so the harder these things fly, faster these things fly around, the more often they bash into things, the harder they bash into them, so the more pressure they apply, so the more space they take up. So as we've cooled this down, we've taken energy out, pressure's dropped, so the bottle's been crushed by the air pressure around it.
But the other ones that don't have a lid on, presumably they must have pulled in extra molecules?
That's right. The air pressure will just push extra air in the top of the bottle, so there should be an extra 10% of air which has got inside that bottle. We have a nice little experiment to show that in a bit more exciting way. So what I've got here is a couple of 2p pieces. You basically just want a coin which was bigger than the neck of the bottle. I'm going to cover one side of it with a bit of loo roll or a bit of tissue. And I'm now going to make this tissue really wet, so sopping wet.
In fact, it's so wet that the tissue's gone transparent. It hardly looks like there's anything there at all.
So while the bottle's in the freezer, we're just going to put the coin tissue side down onto the bottle, shut the door of the freezer and leave it for about half an hour, which should then mean everything freezes nice and tight and possibly seals the top of that bottle.
We'll come back after that's had plenty of chance to freeze and find out just what happens.
So get yourself an empty plastic drink bottle without the lid, some tissue and a coin. Cool the bottle in the freezer, put the tissue over the coin, wet it and put it onto the open neck of the bottle, then put the bottle back in the freezer. We'll catch up with Ben and Dave later to find out what happens.
David's standing by on the line. He's in Norwich. He wants to talk about Chernobyl and anything that has been discovered there in the wake of what happened more than 20 years ago. It's almost 30 years, isn't it, what happened in Chernobyl? Let me pick up first, though, with an interesting story which I spotted this week about chronic fatigue syndrome. Now, this is a disease of unknown etiology. What that means to doctors is we don't know what causes it or how it actually achieves the symptoms that it does. The constellation of symptoms that people who have chronic fatigue syndrome also goes by the name ME, which stands for myalgic encephalomyelitis. What this disease does is to cause people to have unexplained symptoms of exhaustion. They get muscle pains, headaches, sometimes there's disturbed sleep, and just feel cognitively slowed sometimes, and no one has ever managed to pin a cause on this. There was some speculation a couple of years ago, to much acclaim, that a virus called XMRV, which is a mouse virus, might be causing this, but subsequent tests have ruled this out. They can't find evidence of this virus in people who have chronic fatigue. And then this paper's come along. It's in the journal PLOS ONE, and it's by Olaf Meller and his colleagues. They're at Hawklands University Hospital in Bergen in Norway. And it started because a while back they had a patient who had a disease called lymphoma, which is a kind of cancer of white blood cells, specifically B lymphocytes. And there's a very good drug called rituximab, which is an antibody you can give, which kills B lymphocytes. So if you give this to someone with lymphoma, you can get rid of all of the lymphoma cells in the body. Now, by sheer chance, this patient also had a history of chronic fatigue syndrome. They gave the patient the rituximab drug, and his lymphoma was controlled. But the patient said, this is amazing. All my symptoms of chronic fatigue have vanished. And the team was so intrigued that they decided to set up a clinical trial, which is what they're now reporting. And they got 30 patients who had a history of confirmed chronic fatigue syndrome. And they randomised them into two groups of 15 patients. So this is small groups. You've got to be cautious how you interpret this, but it's two groups of 15 patients. And half the patients they put on a placebo. The other half they gave this rituximab drug to. And they then followed them up, and no one knew what anyone was getting, and they were assessed subjectively. They were asked, how are you feeling? And they were also assessed in terms of their function by a physician. And 10 of the 15 people in the rituximab treatment group had resolution of their symptoms, compared with only 1 in the placebo group. So quite a dramatic response. It didn't kick in, surprisingly, until 3 months after the drug was given, but you can demonstrate all the white blood cells go away almost instantly. The team think this is because part of the disease is caused by antibodies in the bloodstream and cells that make antibodies. And it takes time for those antibodies to dwindle after you get rid of the B cells and the longer-lived plasma cells that make the antibodies.
And that's certainly very good news, but I imagine killing all of these white blood cells won't do very much for the human immune system.
Well, you're right that it does leave you relatively immunosuppressed. But the good news is that you do still have these antibodies in circulation. You can still regenerate the B cells sometime down the road. And with appropriate vaccination and health care, there's no reason why you shouldn't do very well. None of the patients had any major severe immunocompromised type outcomes in the study. So although that's a risk, it doesn't seem to be too severe or too much of a risk, at least in this study. But again, caution here, it's a small study and it's initial, and we don't actually know why taking these B cells away has made these patients so much better. We also don't know why the 1/3 of the group who got the treatment didn't get better yet, but I guess it's a starting point, and regardless of actually what happens, we now have a window into this condition. We can try and work out how to make people better. Now, moving on, it's our Naked Scientist Science Phone-In this week. It's Chris Smith, Dominic Ford and Emily Seward. We're answering all your science questions. David's in Norwich and wants to talk about nuclear reactors and things. Hello, David.
Good evening. Good evening.
Far away.
Well, as I witnessed our very first true nuclear explosion on Christmas Island, which was Grapple X, 1.8 megaton bomb, and I know the effects that it had on wildlife out there. We had the job of clearing up afterwards, blind and dead birds, fish, crabs even, had to be incinerated. I just wondered what had happened to nature at Chernobyl, whether there are any comparisons of what happened with the nature around these areas of the explosion at Chernobyl.
Interesting point, David. Obviously, there is a slight difference between a nuclear bomb and Chernobyl because what the two things will produce will differ. And in terms of where they actually deposit the material and over what sort of area, in what sort of form, how soluble it is, how much heat and other radiation is released locally and then at greater distance, those things will all differ between a bomb going off and a test bomb at that in a test site and then a nuclear reactor quite close to the city. Kiev obviously didn't do too well out of this. Really interestingly, they have actually obviously isolated the area around Chernobyl, and there are some real bad hotspots in there where if you go and take samples, you will find that plants and soil samples are very, very radioactive. People have actually been and had a look at the reactor buildings, though, and there was a very interesting paper, I think it was published in the journal PLOS ONE, a few years back, and they found bizarrely a kind of fungus growing inside the remains of the nuclear reactor. And you'd say, wow, how on earth can that happen? And actually this fungus is very interesting because it's turned on lots of genes that make the pigment melanin. And melanin is the same stuff that makes us have brown skin and a suntan, and it's there as a way of soaking up ionizing radiation or energetic rays which could damage our DNA. So by the yeast making itself very, very dark, it has its own inbuilt body armour against radiation, and in this way it's able to resist a lot of the insult of the radioactive environment. So this is one interesting example of if you apply enormous selective pressure to nature, then you can actually get some quite interesting things happening. And so it's a really useful study area. Even though it's not necessarily a great thing to have happened, it gives us an insight into what can happen and how nature can respond in this sort of environment. I guess the plants, Emily, must be doing some interesting things as well.
It's true. So plants can actually incorporate radioactive isotopes into their bodies. So radioactive carbon-14 is actually used to study the plants and see how they distribute carbon around their bodies. So yes, the plants in that area would also be affected.
I suppose it's also worth mentioning some scientists are looking at modifying plants to make them soak up some radioactive chemicals from the soil better and put them into insoluble forms so they get locked away in the plant, and then you can clean up the soil by just harvesting the plants and destroying them. Basically, you get the components that are radioactive now in the plant. They're like a hoover sucking the things out of the soil, and it's a good way of cleaning up soil without having to cart the soil away.
Yeah, no, and they're also looking at doing that for other toxic compounds. So if you've got lead in the soil, you can have a special type of currently slow-growing plant, but they're working on that, and it takes up the lead and cleans up the soil.
Super, thanks Emily. Right, now, I suspect you're one for household gadgets, but I bet you haven't come across one of these. A digital kitchen that teaches you to cook in a foreign language. Jane Rex, been to see what's on this particular menu.
Bonjour et bienvenue dans la cuisine française.
If conjugating verbs isn't your idea of an interesting way to learn a language, the latest research at Newcastle University could be just the thing for you. Language experts and computer scientists have developed an innovative kitchen that gives lessons in cooking and French at the same time. It tracks your actions with motion sensor technology and it speaks to you as you prepare your dish. Professor Paul Seedhouse is involved in the linguistics side of the project.
This research has been based on previous research done by my colleague Patrick Olivier in computing science in Newcastle. He developed a digital kitchen for people with dementia. So, for example, if they left the oven on for too long, it would tell them to turn it off. And when I saw that, I thought that the technology could be adapted for use with language learning and teaching.
Très bien. Commençons à cuisiner.
When you enter the kitchen, it looks pretty much like an ordinary kitchen. Some of the differences you'll notice if you look at the kitchen equipment, the handles are larger than normal. That's because they have sensors embedded. And this technology you may be familiar with already. It's similar to Nintendo Wii technology. So there are sensors and they detect movement in all directions. The kitchen will then speak to you in French.
Pesez 100 grammes de farine.
Weigh 100 grams of flour. When you're actually doing the cooking, you have a number of alternatives open to you. You can request a repetition, or you can ask for a translation, or you can pause the programme, you can go backwards and forwards. But a really important point about this learning environment is that we put people in pairs. Typically, one person's better at French, one person's better at cooking, and that means that they transfer the skills and they help each other to learn.
Aujourd'hui, nous allons cuisiner un clafoutis aux poires.
The recipe we've got is called pear clafoutis, and it tells you first of all to peel the pears. So first of all it tells you to take 4 pears, and the system then detects that you've taken the package of pears and you've moved it onto the work surface. It then tells you to take the peeler, and so the sensor in the peeler will then detect that you've taken it over, it's been moved, and then the system will then detect whether you've made the correct peeling motion with your peeler on the pears. When you've done that, it'll tell you to cut the pears into 4. So then it'll look and see, have you taken the knife? Has the knife moved over to the surface? And then have you made the correct chopping motion with the knife? If you don't make a chopping motion with the knife, let's say you move it from side to side, it won't detect that as correct, and so the system will loop back and give you the instructions again.
N'oubliez pas la farine.
Don't forget the flour.
Dan Jackson and Jürgen Wagner are involved in the technical aspects of the project. They explained more about the small sensing devices that are embedded in the kitchen utensils.
Fundamentally, we're interested in understanding how the objects are used and how they've been manipulated. We've developed this hardware that actually detects the motion, uses something called an accelerometer, which is a device that measures acceleration.
The accelerometer inside tracks the smallest movements you do with your hands, the smallest movement you do with the utensils. These are called also motion primitives. And this information is sent over to a computer which acts as a base station. And this base station translates these simple activities, these motion primitives, into something more meaningful in, was it a chopping activity, a steering activity, or whatever activity we can measure.
So, for instance, if you pick up a utensil, the device will wake up from a sleep state and it will start broadcasting its motion to the computer. And then on the computer we can analyse that information and work out what that object has been used for. Chopping with a knife would give us a different signal to someone scraping or slicing with the same knife.
90 grammes de sucre.
Is that 80 or 90?
90, I think 90, 90.
Yeah, 90 grams of sugar. Wait, careful, wait.
Bon.
C'est bon.
Et voilà, vous avez terminé.
As well as making learning fun, Paul Seedhouse says the kitchen builds on the proven technique of task-based language learning. There are now further plans to take the concept out to a wider audience.
Well, on the point of view of language learning and teaching, it's unique because it's taking the ideas, the excellent ideas of task-based learning and teaching out of the classroom and, if you like, into the kitchen. So you're combining it with a real-world task. It's also unique in that you're learning two skills at the same time. In other words, French skills and cooking skills. So we already have the full-scale digital kitchen in Newcastle University, but we've now developed a series of portable kitchens which we take out on roadshows. It's basically tablet PC, 6 implements and a pair of speakers, so it's very portable. And we're going to be placing portable kitchens in 4 different countries in Europe and trying them out there.
The research is supported by the Digital Economy programme run by the Engineering and Physical Sciences Research Council. In the future, this way of learning could be used to teach people any number of skills, ranging from nursing to driving. The new type of kitchen could be available for schools, universities and even the domestic market by the end of 2012.
Très bien. Imagine if we did kitchen science with that. We could get Dave in that kitchen. Dominic, can you imagine the kind of stuff we could do there? Kind of educate people in science in French.
Yeah, see what Dave's French is like.
That was Jane Reck reporting from the digital kitchen that teaches you French. And you can find out more about that story on the EPSRC's YouTube channel, which is at youtube.com/EPSRC video. And we'll also put a link to that on the front page of our website.
Laying the facts bare. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, Emily Seward and Dominic Ford. Dominic, I like this question. Robert McCulloch, Conrad Webb says on Facebook, excluding its construction, what has the LHC, the Large Hadron Collider, actually contributed to science so far?
Well, it's quite interesting from my point of view because I did a physics degree 10 years ago. And I think one of the main things that's come out of the LHC so far is actually disproving many of the theories that I learnt 10 years ago as being very probably correct. There was a theory called supersymmetry, which people were very fond of a few years ago and they thought was very probably right. But in fact, the LHC hasn't found evidence of those particles and the theory essentially appears to now be completely wrong. Obviously, you've heard a lot about the Higgs boson, which is the mechanism by which we think particles acquire mass. And the LHC hasn't definitely detected that yet in some of the places where it might have expected to see it, but there are still places where it could be. The LHC is a long-term experiment, and I think in the next few years it's going to really see what theories are correct rather than what it's done so far in disproving some of our previous ideas. So I think stay tuned.
I also think that when you have big investment in big projects that have to solve a lot of project problems to deploy and develop that project, you inevitably produce spin-offs that would otherwise not have come about. And I think one of the good ones, Peter Quinn, who I think you met in Western Australia,
yes,
who's heading up the Australian bid for the Square Kilometre Array, made the point to me that actually, the World Wide Web came from the grid that was assembled at CERN because of particle accelerators and physicists needing to share huge amounts of data. That probably wouldn't have happened, at least at the rate it has, were it not for the need to share that data because of something that could produce a huge amount of data. So I think it is kind of important, isn't it? Now, Emily, let me just ask you, because there's an interesting paper this week looking at reefs and why they recover so badly, and it turns out it's all down to seaweed.
Yeah, no, that's right. So seaweeds, which are also known as macroalgae, can unleash a chemical arsenal which is toxic to the corals, which might explain why the damaged reefs are recovering so poorly. So writing in PNAS, the Georgia Institute of Technology researcher Douglas Rasher and his colleagues studied the sensitivities of 3 different coral species to 8 different types of seaweed. They would bring the two together, as might occur in a coral reef, and this resulted in bleaching of the coral, reduced photosynthesis, and even death. So the physical proximity wasn't the cause, the scientists confirmed, because when plastic models of the offending macroalgae were substituted for the real thing, the corals remained healthy. Instead, it turns out that the seaweeds secrete a cocktail of oil-soluble chemicals called terpenes. These can rub off on the corals, killing them. The seaweeds most likely use the chemicals as a means of antimicrobial defense, but corals can lose out when the reefs damaged by human activities and climate change are then invaded by the macroalgae. This is allowed because they can gain a toehold as the fish that would normally eat them, the herbivorous fish, are not there because of the damage to the environment. And this, say the scientists, may well explain the poor rates of recovery seen on many damaged reefs.
Well, that's fascinating. So you damage the reef, the fish go away. If the fish go away, they don't eat the seaweed, so the seaweed overgrows, and the seaweed poisons the coral, which is trying to regenerate, so it's a vicious circle and the reef never gets better.
Yeah, no, that's right. So it's not that they're trying to kill the coral, but that it's a side effect.
Gosh, so what's the sort of scale of this? How much reef loss is there?
Well, it's actually a much bigger problem than people realise. The rate of tropical rainforest loss is always talked about, but the Indo-Pacific reefs are shrinking at 1% a year, so we're actually losing the reefs at a faster rate than tropical rainforests.
Well, that's a worry, isn't it? Is there anything we can do about it?
It's very difficult, so you've got to try and keep the reefs very clean and also try and reintroduce the fish that can then eat these seaweeds, and that's one way of dealing with it.
Well, let's hope so, because, of course, reefs aren't just about pretty fish and marine wildlife. I mean, they sustain whole communities and things as well, with people exploiting them for fishing and all that kind of thing. And if it's done sustainably, then they're a huge asset. But if we destroy them, it doesn't look like we're going to get them back very easily. Dominic?
Now, Chris, we've got a question here which I think is for you. We've got the cold winter weather descending, and no doubt the pavements and roads will be getting quite slippy soon. But why are ice and snow so slippery?
That's a very hard to answer question, actually, and in fact it's the source of a lot of disinformation. In fact, if you have a look in many texts and books and things, especially historically, you will find they claim that when you have an ice skate, for example, on an ice rink, the pressure of the ice skate pushing down on the ice causes the ice to increase its temperature because it's being compressed, and it melts a bit, and this puts a layer of water on the surface of the ice, and that means the ice skate then slides along. Doesn't kind of stand up to scrutiny, though, because people wearing shoes where the same weight is distributed over a much bigger area, therefore with much lower pressure, still slip over on the ice. And in fact, if you plug the calculations through, the numbers into the calculations, you find it actually only changes the temperature of the ice by a fraction of a degree. So this cannot account for why ice is slippery. It can't be a melting phenomenon. And what scientists actually think is going on is that probably because you have an ice surface and there will be water molecules on the surface which are not tethered to other water molecules, they exist more as a liquid than as a solid. So all ice is covered in a very thin at a molecular level layer of water. And Michael Faraday showed this quite interestingly because he got two ice cubes, which are both slippery, put them together, and they stuck. Now, if there wasn't water there, then they wouldn't have stuck together because obviously the water then froze onto both. So what scientists think is going on is that there is a very thin layer of water on the surface of any ice surface, and it's that water that acts as the lubricant and reduces the level of friction at the surface. So I think that's probably the best explanation I can come up with.
Does that depend on the temperature of the ice?
Well, to a certain extent it will, but at the same time, if you've got atoms, which are molecules of water, which are sitting on the surface of the ice, which are untethered and unbonded to other surrounding molecules, then it's easier for them to have energy and detach and form a water film than it is for molecules elsewhere in the ice to move around. So it favours the formation of a layer of water at that point, which could make them slippery. How about this one for you then? Can you help me with this? Kevin Fitch says, how can we tell the temperature and makeup of a distant star? I've heard that observations of electromagnetic spectrums may be used to determine the composition of stars, such as how helium was discovered in the sun. But you can also use this to determine the temperature of an object. So how does both apply?
First of all, to measure the temperature of a star, it's really about the colour of the star. If you take a piece of coal, for example, and you set fire to it, as it gets hotter, it will start to glow red hot, and then perhaps it's very hot, it will start to glow yellow hot, and then in intense fire, it will start to appear white or maybe even blue. So by applying that logic back to a star, a blue star is a hot star, and a red star is a cooler star.
What about what's in the star?
Now, what's in the star is more difficult. But different elements emit at very specific wavelengths and produce what we call spectral lines. And if you have a spectroscope that splits up the light of that star into different colours, you can see that certain colours are either not present or there's a huge amount of light at that particular wavelength. And that tells you there must be atoms of a particular element emitting light in that star, so you can tell what that star must be made of.
Terrific, Dominic. Thank you very much. In fact, Robert Bunsen was the forefather of the science of spectroscopy. So Bunsen of Burner fame also discovered that you could work out what things were by looking at the certain absorption pattern they make and what wavelengths of light they soak up. And ironically, after working for many, many years in his laboratory on identifying some rare compounds, he unfortunately left a big sheaf of notes with 10 years' work in the sun in his lab, went off to the pub. Well, I don't know he went off to the pub, but I suspect he went out for lunch, came back and the sun set fire to it, and he lost the lot and had to start all over again. But he was a very good scientist and he did the whole lot from scratch. Emily, Theo is in Essex and says, I've been wondering, how do plants cope with virus infections? Is it similar to what humans do?
Well, that's a really good question, and there are some fundamental differences. So viruses spread around animals mainly by lysing the cells, and then they can go on and infect another one, whereas they spread around plants via little pores called plasmodesmata. And so one of the main ways that plants have to deal with viruses is by closing these plasmodesmata. They can use callose or they can use other proteins to block them off and stop them spreading. And they can also do this in the sieve tubes, which are the connective tissues around the plant. But in a similar way to animals, plants can also respond to viruses with a hypersensitive response. So this is where the plant cells actually die, they sacrifice themselves, and this is a good way of trying to stop the virus spreading. And they don't have antibodies, which is a big difference again with the animals. But some scientists are trying to engineer in plantibodies. So, for example, tobacco expressing antibodies to the coat protein of the grapevine fanleaf virus have been shown to be somewhat protected from infection by that virus. But I think a very key way in which the plants deal with viruses is using small interfering RNAs, and these target double-stranded RNA, which is unusual in a normal plant cell, but a common thing to find if they're infected with a virus.
And that's quite similar to humans, because Theo asks, is it the same in humans? Human cells also can detect when they have virus genetic material inside them, usually because it doubles up and forms this double-stranded RNA, and that triggers the cell to unleash a whole cascade of mechanisms that it uses to defend itself, including killing itself and also secreting factors called interferons that put other cells nearby on the alert, making them much less infectable. Well, here's something which I spotted this week, which I thought was very interesting. There's been this story knocking around for a while that Alzheimer's disease, the dementing illness that people tend to get when they're older, and which is reaching very high levels as people live longer in the modern world. This may actually be linked to the herpes simplex virus, the agent that causes cold sores. And rather worryingly, 80% of the population are infected with herpes simplex virus. So knowing whether or not this is a real risk factor and what we can do about it is pretty important. There's a lady called Ruth Itzhaki who works at Manchester University, and she's got a paper in the journal PLOS ONE this week in which she's built on a number of observations she's made over a long time into this very topic. And the sort of evidence linking herpes simplex and Alzheimer's is that if you look in the brains of people who have Alzheimer's disease, you find these proteins, aggregates called beta-amyloid plaques. And very often you can find herpes simplex DNA associated with them, suggesting that the virus was there at the scene of the crime. Also, biochemically, when cells are carrying or infected with herpes simplex, they increase the production of the protein that makes these beta-amyloid plaques, and also these neurofibrillary tangles, one of the other pathogenic hallmarks of Alzheimer's disease. So there's the smoking gun, but how is it actually linked to the disease process? That was the question they were asking in this paper in PLOS ONE. And what they've done is some very nice in vitro, in other words, in the dish tests, where Ruth Itzhaki teams up with a guy from Glasgow called Chris Preston, who has made a whole bunch of mutant or genetically strange, I'll rephrase that, a whole bunch of mutant forms of herpes simplex where they've deleted certain genes from the virus that interrupts the virus life cycle at various stages. So they can then ask the question, well, which aspect of the virus going into cells actually trigger this Alzheimer's provoking process? What they found is that it's actually when the virus copies its DNA. And this is both bad news and good news. The good news side to this is that there's a very good drug. It's called acyclovir, which many people who've had cold sores will have used because it's in the cream Zovirax. And acyclovir stops herpes simplex from copying its genetic material. So although they've only proven this in the dish so far and shown that if you dose cells with acyclovir, they produce fewer of these tangles, and they also produce fewer of the proteins that can make these plaques, it's still very encouraging because it suggests if you put old people on these agents, then you could reduce their risk of going on to develop Alzheimer's disease subsequently, and they're not very expensive. And if you look at the cost of caring for someone with dementia versus the cost of giving people a drug which is viewed as relatively safe, it could actually be a really good way to cut down the rates of what's going to become an extremely large cost burden for the NHS in future.
Yeah, no, that sounds very important, and it's the protein aggregates which are the hard bit to deal with, because once you start them forming, don't they sort of self-perpetuate and build on each other?
Well, we don't actually know whether that happens to a greater or lesser degree. What people actually think probably happens is that once you've got some of them, they injure adjacent cells, and this makes the cells develop a stress response which make more of the chemicals that make more of these plaques. So in some respects they do perpetuate or potentiate their own production, but it's not because they actually make more plaques, it's because they make cells make more plaques. If you make the cells make fewer of them in the first place, then that should slow down the rate at which the disease has its onset. The interesting thing, though, is that you say, well, if 80% of the population carry herpes simplex, why haven't we all got Alzheimer's disease right away? And the evidence is that although it's present from a young age in the majority of us, you just acquire it from a kissing parent usually, it doesn't actually go into the brain until you're much older. It stays in the peripheral nervous system. And what scientists think happens is that as you age, the immune response becomes less effective. And so the virus is able to gain a toehold in both the central and peripheral nervous system. It's more likely to get into the brain, albeit in a limited way. And it's that entry into the CNS, the brain, that then increases the risk of Alzheimer's disease later. So therefore, putting people on these drugs might stop that happening. It might reduce the risk of them having problems.
And do they know at all why they are more likely to go into the central nervous system when they're older? Is it decreased immunity, or is there something else we can look at?
Yeah, we think that because as you get older, your immune system just becomes a bit less effective at controlling everything. Shingles, for example, which is caused by varicella zoster virus, the chickenpox virus, that's another kind of herpes virus. This becomes more common as you get older, and we think it's because the immune system just becomes less good at controlling infections. So these viruses that live with you for life then begin to get into places that previously your body would have had no problem warding them off. Now it's less good because you're older, so maybe you need to pop a pill. Jeff's on the phone. He's in Shenfield. Hello, Jeff.
Hello.
Far away.
As there are now a number of space probes on Mars, I wondered if it would be possible to detect a transit of the Earth across the Sun from Mars, whether in fact it happens, and if it does, how rare it is, because we know that a transit of Venus is pretty rare and occurs, once every 120 years or so.
It is incredibly rare for that to happen because the Earth is so much further out in the solar system than Venus. So it's a very small target that you're trying to get across the surface of the Sun. I think a transit of Mercury across the surface of the Sun has been seen by one of the Mars rovers. I'm not completely sure on that, but Mercury does transit the Sun quite often, but Venus and Earth much more rare.
Scientists did see the first Martian shooting star in recent years because one of the pictures taken by one of the bodies, one of the orbiters on the surface of Mars, showed a lovely shooting star in one of the frames, which was reported in one of the science journals. Well, now with a look at what else has been making scientific headlines this week, with our Naked Scientist news flash, here is Mira Senthilingam.
The world's first commercial spaceport has opened in the deserts of New Mexico. Targeting all budding astronauts, Spaceport America is Virgin Galactic's gateway into outer space, providing members of the public 5 minutes of weightlessness up there at a cost of £127,000. The eco-designed building will house 7 spaceships, mission control and a visitor experience area for those that can't afford the flight itself. Sir Richard Branson spoke at the launch.
These beautiful ships will shortly be ready to welcome the first of more than 450 people paid up and waiting to fly. The building has achieved the LEED Gold standard using local materials and regional construction techniques. And we have minimised energy requirements through the use of geothermal heating and cooling and extensive energy management practices. Simply put, it's a 21st century building for a 21st century business.
A new test could significantly boost the success rate of IVF treatment. The technique, developed by Dagan Wells and his team at the University of Oxford, screens potential embryos for chromosomal and genetic abnormalities before they're implanted, improving chances of pregnancy by up to 70%.
The embryo that looks the best can often harbour lethal genetic abnormalities. So the new test really combines a bunch of different aspects of embryo biology assessment. So we're looking at the chromosomes, we're looking at the mitochondria which power the cell, we're looking at the telomeres which protect the chromosomes, and together that's giving us a very deep insight into the health and biology of the embryo.
A vaccine against malaria could be on the horizon, after promising results from a clinical trial taking place across Africa. The RTSS vaccine is the most advanced malaria vaccine to date, currently targeting children under 18 months of age. Involving over 15,000 participants across 7 African countries, preliminary results published this week from the Phase 3 clinical trials found that infants receiving the vaccine had about half the risk of developing malaria than those without it. Chiri Abanyega is principal investigator on the trial site in Ghana.
Our results showed that RTSS reduced the risk of children aged 5 to 17 months experiencing clinical malaria by 56% over a 12-month follow-up period. The study also found that RTSS reduced the risk of severe malaria by 47%. This is remarkable when you consider that there has never been a successful vaccine against the human parasite.
And finally, new insight into the eating habits of the giant panda. Unlike other meat-eating bears, the giant panda is an omnivore with a diet consisting mainly of bamboo, eating up to 12 kilograms of the plant every day. But their ability to digest the cellulose and hemicellulose fibres dominating a bamboo plant has long been a mystery, as they lack the digestive enzymes found in other herbivores. Using gene sequencing techniques, Fu Enwei and his team at the Chinese Academy of Sciences identified the presence of unique enzymes and gut bacteria, helping pandas make a meal out of this low-nutrient plant.
We found in the panda some special bacteria who could help the panda digest this kind of fiber. Also, we found the genes coding for enzyme to do this kind of job. Bamboo nutrition is very low. They contain low protein, sugar, and fat. So the panda needs to get some part of the nutrients from the fibers.
Despite this aided digestion, the bamboo remains low in nutrition, explaining just why the pandas have to eat such a large amount of it every day. And so the reason they choose to eat this above other foods still remains a mystery.
Well, that's food for thought. Thanks, Mira. The transcripts and references for that and all of the stories we've covered this week are on our website at thenakedscientist.com/news.
Got actually a Facebook message here from Olga Iljikiova. I hope I've said that right, Olga, who's listening in York, and says, speaking kitchens, come on, there are cheaper and more efficient ways of learning a language and how to cook. Also, this only covers a tiny section of the vocabulary, but you learn the vocabulary of delicious food, and that can speak volumes, surely.
Distilling the best science. The Naked Scientists.
It's The Naked Scientists with Chris Smith, with Dominic Ford and Emily Seward. Very quickly, Emily, C.B. Axel in Second Life says, how do you safely destroy plants?
Well, I would say that if he's talking about the radioactive ones we were referring to earlier, he'd have to go collect them in a suit and then burn them down, collect the residues and dispose of them safely. If you were talking about another plant, then normally if you're genetically modifying them, you autoclave them and kill them that way.
Terrific. Thank you, Emily. Right, well, we asked you earlier to do a bit of experimentation. Well, let's go back to Ben and Dave and see what happens as they thaw out those bottles they were freezing earlier.
We're looking at some interesting aspects of air pressure today, using only used plastic bottles, a coin, a bit of tissue and your freezer. Earlier on, we asked you to take a plastic bottle, a half-litre fizzy drinks bottle is perfect, take the lid off and put it in the freezer for a while to cool down. Then once it's nice and cold, we asked you to put a coin wrapped in wet tissue on the top and put it back in the freezer.
The next step is to take the bottle out of the freezer and heat up the air inside that bottle before the water at the top melts.
Right, so in order to heat it up, what do we do? Put it on the oven, put it in hot water, in the microwave? How do we do this?
Hot water would work, probably slightly better, but your hands should be fine. Plenty of heat in your hands.
Okay, so let's go and grab our bottle. And we can see, looking at the top of it, that the tissue has clearly frozen. That's definitely ice now that's wrapping the coin.
That's right, so hopefully there shouldn't be any gaps in there and it should work quite nicely. You might want to do a couple of these at once because they don't always work, so we'll see whether this is a good one.
Okay, now the bottle looks a little bit frosty. Is it cold? Is it all right to handle?
It's cold, but okay to handle. I'm just going to wrap my hands around it, heat it up, so the air molecules in there are getting hotter and moving around faster. They're bashing into the walls harder and harder and harder, applying more and more pressure to this bottle until hopefully...
Oh, wow, so the coin that was wrapped in wet tissue has just fallen off the top, but not just fallen, it popped off. It actually got flung across the room, certainly a couple of feet.
That's right, the pressure increased and increased and increased until something broke. And then when it did, all that air escaping pushed the coin on the top a couple of feet into the air, and it made quite a satisfying pop, I feel.
This obviously tells us something about the very basic aspects of gases and the fact that they expand when you heat them up and they contract when you cool them down. But what use is this actually demonstrating?
Well, this is used all over the place. For example, when you drive your car, what's happening there is you ignite some fuel in some air, it gets incredibly hot, it expands maybe 30, 40 times, pushes a piston down in the cylinder, and that's attached to the wheels and drives you along.
I'm quite a conscientious recycler, so whenever I have had plastic bottles in the house, I tend to rinse them out in the sink and then put them in my recycle bin. And I've noticed before that if I rinse it in warm water and then I put the lid on, then quite often those bottles can crush themselves. Am I seeing exactly the same effect, but in the opposite direction?
Yeah, it's pretty much the same effect. You put in really, really hot water in there, so you're going to get very hot air, which will shrink as it cools down to room temperature. But also there'll be a load of water vapour in there. And when water vapour cools down, it will condense on the side of the bottle. You've probably seen that. Then it's shrinking by a factor of about 2,000, the water vapour, when it turns into a liquid. So you get a much bigger shrink, which can be really useful. For example, in steam engines going the other way, you boil water, it expands by a factor of a couple of thousand and really pushes those pistons along and drives your train along.
So a change in temperature will cause a change in volume by a few percent, but the change that causes it to transition from a vapour to a liquid, that seems to make a really big difference.
That's right. If you just think about the densities of a gas versus the density of a liquid, air has a density of about 1 gram per litre, whereas water has a density of about a kilogram per litre. That's a huge change in volume to go from one to the other. And so this change in volume with temperature is the basis of most of the ways we generate energy in our society, ranging from cars to power stations.
And all of that we can see just from putting an empty plastic bottle in the freezer with a few pennies on top. That's all we have for this particular experiment, but as always you can find loads more to do, including videos and pictures online at thenakedscientists.com/kitchen science.
Thanks, Ben and Dave. And as Ben mentioned, you can find out more about their experiment at thenakedscientists.com/kitchen science.
Emily, thank you. Well, now it's over to Diana O'Carroll for our uplifting or perhaps even weightless question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week, how feeling heavy keeps you feeling good?
Hi, I'm Matt from Norwich. I was wondering, what is the minimal gravitational force required to keep astronauts healthy during long space voyages? Would it take 1 full G, or could we get away with less?
Being left in space can lead to muscle wasting and osteoporosis. Here's Dr. Kevin Fong, who's co-director for the Centre of Aviation, Space and Extreme Environment Medicine.
That's an excellent question, and the answer is probably. The problem with long-duration spaceflight is that microgravity has a range of very negative consequences for the human body over extended durations. And when we're talking about going to Mars, missions that may be up to 1,000 days in microgravity or only partial gravity, the big question is, how do you protect astronauts during that time? And you've got 2 options. Either you go quickly and reduce the exposure to microgravity, or you put up with the long-duration stay in space and you introduce a countermeasure, and that countermeasure should be artificial gravity. They've experimented with what might be the best prescription for gravity. You can think of gravity like a drug. Certainly on Earth, we are not constantly exposed to an unchanging 1G environment. When you run up and down a flight of stairs, you shock load your joints, and you get more than 1G loading at load-bearing areas during exercise or impact. When you're asleep and you're lying horizontally in your bed, along the vertical axis, your body is essentially perpendicular to the gravitational field and so is gravitationally unloaded. And indeed, that's how we simulate microgravity here on Earth. We put people in bed and tilt them 6 degrees head down. So what is the dose of gravity that would work? And I was involved in a pilot study that suggested that if you lay someone down on a short-arm centrifuge and you centrifuge them at a rate of about 40 revolutions per minute, on a device that has a radius of about 3 meters, that provides sufficient loading, if you do it only twice a day in 2 one-hour doses, to protect a lot of the systems of the body, but not all of them.
So, centrifuging astronauts in a wheel similar to the ones you find at the fairground may be one way of counteracting microgravity and its effects. On the forum, Clifford Kay said that, given gravity varies slightly across the Earth, it should be expected that humans can tolerate some differences. But more research is needed to find out if an environment with less than 1G will still be sufficient to maintain good health over time. Next week, why not grow a moustache to answer this question?
Hello, I'm Damon from Blackburn. Do cats' whiskers and human facial hair have anything in common in terms of their uses?
Cats are said to use their whiskers as sensors so that they don't climb into a space they won't get out of. Now, have you ever seen a human do the same thing? Answers to Chris at thenakedscientist.com. You can join in the discussion at the forum, which is at thenakedscientist.com/forum. You can Twitter at Naked Scientists, or you can join the Naked Scientists Facebook page.
Diana O'Carroll. Well, that's it for this week. Thank you to our production team, Tom Simpkins, Mira Senthilingam, Ben Vousler, Hannah Critchlow, and others, and you, of course, for sending in your science questions. Next week, we're dipping into gene therapy. We'll be down in Brighton because it's the British Society for Gene Therapy's annual conference, and we'll be reporting live. And just to finish off, CB Axel and Princess Nikki, Emily, were very impressed with your performance this evening. For a first time, they say it's great. Good night.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.